About tangential and normal components of acceleration. And before I begin, there's a small thing I have to prove before I talk about the other points. So, so here's a statement. Let's say you have a vector valued function. So RT is like you have a particle moving in space or in 2D. At each point in time, it resides some point. So you can think of RT as taking a real value and giving you back a vector, a position vector. Okay. Now, if it happens that regardless of the t value, the value of the norm doesn't change, then it will always be perpendicular. That vector value function will always be perpendicular to the derivative of that. And the proof is the following. Let's just say that constant is c, which means norm squared will be c squared, some constant. And then you can rewrite this norm squared as the dot product of the vector with itself. Okay? And since this is true for all time, if two sides of an equation is true for all time, then you're allowed to differentiate and the derivative will still satisfy an equation. So what we're going to do is we're going to differentiate both sides. And while this is not the regular multiplication, there's a dot product version of the product rule. Okay? So you can show that this is the same thing as applying the product rule. Whereas on the right side, it's just a constant, so if you differentiate, you get 0. And then because dot product is commutative, right? Cross product is anti-commutative. You switch that's two sides, it gives you minus. Dot product, on the other hand, you can switch those two, nothing happens. It's the same as before. So you can switch this around and write down RT dot R prime T and see that this plus this are exactly the same thing. And then if you divide both sides by 2, cancels. Now what does it say? You have two vectors, their dot product is 0, that means
They're perpendicular.
they're perpendicular. So that's the end of the proof. Okay, and you can say QED. That means this was what was to be proved, and it has been proved. Okay, so that's going to be a small fact that we're going to use a little later. But let's go back to an example that we tried to do last time. RT equals to say t squared t cubed. And we just took that. Okay. So find a unit vector tangent to RT at all times. At each time t. At each time t. Now we already know how to get a tangent vector. How do you get a tangent vector for a vector value function? Remember, we're thinking of this as a moving particle, but moving particles have trajectories, so you can also think of this as a curve in 3D. At each point in the curve, you can talk about a tangential vector. Right? This vector could be long or small, or it could be in the other direction. So there are many different vectors that are tangent to this vector. But what's like an efficient way to get just one tangent vector? Yeah.
Maybe the derivative.
Yeah, you just differentiate, and that gives you the velocity vector, which is always tangent to the trajectory, right? So if I take vt, which is the derivative of this, that's going to be 1, 2t, 3t squared. That's going to be a vector that's tangent to it. So is this the answer? Well, not quite. Why is it not the answer? What does it not satisfy? What does this not satisfy the condition? Yeah?
Is it perpendicular to?
No, that's not that. Yeah?
Like you need time for it.
It does have time. It does. At each time, it's
Oh, it's not a unit vector.
it's not a unit vector. You have to make it to be a unit vector. How do you make anything to a unit vector? Divided by its size. So now what you write down is t for tangent, and since it's a unit vector, you put a hat. So tt is 1, 2t, 3t squared, and you divide it by size, which is square root of individual things squared. Okay, and that's going to give you, well, something crappy. So I want to put it inside. We'll just leave it like that. Okay, so we'll put it as 1 plus 4t squared plus 9t to the fourth. Okay. So this problem demonstrates a nice formula which says if you want a unit tangent vector to a curve, what you need to do is you have to differentiate r and just divide it by its size. And this is another one of those formulas that you should never try to memorize. People who memorize this formula, when I grade the exams, they'll often do r prime t divided by the norm of rt. Like that clearly shows that this person just tried to memorize the formula and has no understanding whatsoever. See, the problem with calculus 3 is that often there are many, many formulas, and it seems like, oh, it's just plug and chug. You have all these formulas, you just plug them in, and there comes the answer. And the practice exam problems look just like that. So people prepare for the exam thinking, oh, I'll just memorize these formulas and apply. You couldn't be more wrong, because when you actually get to use them in the exam, the formulas look so alike, you forget, do I divide by RT norm or do I divide by R prime T norm? You wouldn't know because you didn't know the concept. But if you had the concept that this is what? This is a unit norm, unit tangent vector, then of course, and you first get the tangent vector by differentiating, and you just normalize it by dividing it by its size. Then there's no reason for you to memorize this. It's just obvious. Okay, that's the important thing. Okay. Now, if you took the norm of t hat t, what do you get? Yeah.
Will it just be the same thing but over itself again?
It's one. Yeah, it's simpler than that. You can get the same result that way, but obviously it's 1. Why is it 1? Because it's called a unit vector. What does unit vector mean?
It's one.
It's 1. Okay, all right. Okay, so if that's true, now we can apply this rule. If you have any vector valued function whose norm is always a constant, then we know that the function itself and its derivative are perpendicular. Okay? So what that tells us is that from this theorem that we just proved, that this means t hat of t is perpendicular to t hat prime of t. Okay. Perpendicular. Now let's try to ask the next question. What would be the size of t prime of t norm? And first you might think, is it 1? And the answer is no. You couldn't, there's no reason for it to be 1. Okay? In fact, this is a really nasty function to differentiate, but so let me first write out what I'm trying to do and then go back to this example and continue on. Okay, so this need not be 1. So we define n hat t to be t hat prime of t divided by its size. Okay. And this one is called the unit normal vector. I told you that normal is just another way of saying orthogonal, perpendicular, right angles. All of them are the same thing. Geometrically, 90 degrees is a very important property. So we know that now you have nt, which is going to be perpendicular to the tangential direction. But because tangential means it's the direction of the curve, we know that this one is going to be perpendicular to the curve. Okay? This one and this one have the same direction, so we know that t hat t and n hat t are going to be perpendicular to each other, and then and therefore n hat t is perpendicular to the curve. Okay. All right, so let's say example 2, I'll just simply say calculate n hat t. Okay, let's see how we can do that. And this is just like so nasty. Well, let's first recall the quotient rule. So the quotient rule is that if you have f over g prime, this is f prime g minus f g prime over g squared. Also, another thing that you should know is that if you have some function inside the square root, and if you differentiate, that's same as 1 over 2 times square root of f times f prime. So we'll be using that. That's because I have to use this one. So because the norm t is defined as t prime divided by t prime, its size, I have to differentiate this function, okay? So let's try to differentiate this. 1, 2t, oh, there should be a squared. 3t squared divided by square root of 1 plus 4t squared plus 9t4. Then you're differentiating this. Okay? And then just by using this, I have to differentiate this first, so it's going to be 0 to 6t times the denominator. 1 plus, let me not write it over here. Let me write on the next line, because I don't have room. 0 to 6t times square root of 1 plus 4t squared plus 9t to the fourth minus 1, 2t, 3t squared times the derivative of this guy. I have to differentiate this, but I'm going to use this formula, which is 1 over 2 times square root of 1 plus 4t squared plus 9t to the fourth. And I need to multiply it by 8t plus 36t cubed. Over squared. Now I can cancel this 2 with both 8 and 36, so that this becomes 4 and this becomes 18. And I can also multiply this thing itself, top and bottom. 1 plus 4t squared plus 9t to the fourth, top and bottom, this sum of 2. I'm not going to write it, but it's the same thing here. And the reason for that is, if I do that, then this will cancel away, and this one will, the square, so that the square root won't be there anymore. So that means I'm going to get 0 to 6t times 1 plus 4t squared plus 9t to the fourth power minus 1, 2t, 3t squared, 4t plus 18t cubed. And in the bottom, it will be 1 plus 4t squared plus 9t to the fourth power to the third power. Okay. Yeah, I'm already regretting my choice. But part of the reason to choose this example was to show how quickly these calculations can be very complicated. Okay? The formulas that I wrote down look so nice and simple that if you don't have enough examples done, often you would mistake it to be a very simple one, but it's not. Okay. So the first one would be negative 4t minus 18t to the third power, comma. That's what I get. If I multiply by 1, there's a minus. And the second one will be 2 plus 8t squared plus 18t to the fourth minus, and then 2t has to be multiplied here, so we minus 8t squared minus 36t to the fourth, comma, and I don't have enough room, so I'll have to go down here. It'll be 6t plus 24t cubed
Let's see.
plus yeah, 54 t to the fifth minus, and then 3t squared must be multiplied here, so it'll be minus 12 t cubed minus 3 times 8t will be 56. 3 times 54 t to the fifth divided by something. So let's simplify. It will be negative 4t minus 18t cubed. 2, these two cancel. 2 minus 18t to the fourth. These two cancel away. And you get 6t plus 12t to the third over something. Now the reason I didn't even bother to write this is one, because it's just too much writing, but see, you're trying to normalize, right? So whether you have this in the denominator or not, they're the same vector. So you can just, instead of trying to take this and divide it by the size of this entire thing, you can just take the top of them, top of this vector, and divide this vector by its size. Okay. So what I'm trying to say is that if you have like vector over A, then what's normalizing this? The normalizing is dividing it by its size. But if you do that, A cancels anyway, so that's the same thing as just V over V norm. So in other words, you just need to look at the top and normalize, okay? So since this is equal to t hat prime t, now we can say that nt hat is going to be, and another thing is that if you see a common factor for the entire thing, you can also take that out. So I see that you can divide everything by 2, so again, negative 2t minus 9t cubed, comma 1 minus 9t to the fourth, comma 3t plus 6t cubed. So this is what I obtained from here by dividing by 2, and now I have to take the square root and do this horrible thing. X squared, 1 minus 9t to the fourth squared plus 3t plus 6t cubed squared. Okay, and I'm not even going to try to simplify this any further. It's just too much. Okay? But that's what NT is. It's important to have some geometric interpretation of what's going on here. So let's go back to what we've discussed so far. I mean, I did some horrible computations. Forgive me for showing you such a horrible computation. But really all we did was that if you have a vector valued function, dividing its derivative by its size, normalizing it, gives you something called a unit tangent vector, and then if you differentiate that one and divide it by size, that gives you the normal vector. Two very innocent looking formulas, which if you actually try to compute it, comes out as like horrible formulas. You really can't help it, because once you divide, if this is not a 1, then you end up with some horrible results, okay? Okay, now, this is a vector of size 1. What does that mean? That means t of t, if you drew on the, well, let's forget the fact that this is a 3D. If this was a 2D vector, what does that mean? It's going on a circle, right? And all it's doing is it's like either it's doing something like that. It doesn't move only on one direction. It could be changing directions as it goes, or it might even speed up or slow down or whatever. But what we know is that if this is 2D, then it's a point that's moving around a unit circle. In that case, what do we know about its tangent vector? Well, tangent vectors are always tangential to the movement, but because the position vector is pointing in a circle, we know that in a circle, the radius and the tangent vector are always 90 degrees, right? That's always true, right? Yeah. So that theorem that I started with, the very first theorem that I started with, which had some proof that contained some things that I didn't even elaborate, is actually kind of obvious if you think of it geometrically. Because if something's moving on a circle, of course, it's going to be perpendicular to its tangent vector. See, this is a tangent vector. This is the vector itself. So that's always true if you're only moving in a circle. Now, think about this in 3D. What about if this is 3D? Well, in 3D, it means that instead of having a circle, you have a sphere. Okay? So you have a sphere, and the tangent vector is just moving on this sphere. It's just moving in any direction. Okay? Again, whatever the curve is doing, it might be doing something crazy on this sphere. At every point, the tangent vector is going to be perpendicular to the radius. So even for the sphere, it's still true that tangent vectors are perpendicular to the radius. Okay? So again, this is true just by geometric intuition, not necessarily by proving it. We proved it by doing some differential calculus and multivariable functions, but it's kind of obvious for this. Okay. Now, but then let's step back. What is this itself? What is this? That's like if you have a curve that's, let's say it's rotating and it's doing something on a 3D curve, then at every point you're going to get a unit tangent vector, okay? So at every point, and the important thing here is that whichever way that this curve is moving, that's the direction of the unit tangent vector. It's never the opposite direction. If the trajectory of this particle is moving that way, then the unit tangent vector must be pointing that way, not that way, because that's these two have the same direction, right? It's not the opposite direction. And this is always positive. Okay? And then think about what this is doing. What this is doing is it's looking at how the unit tangent vector twists, right? This is the rate of change of the unit tangent vector. Right? So this is like moving, and whenever if the unit tangent vector is straight, meaning that if it's a straight line, then this will be undefined because this will be simply 0 and you're dividing it by 0, okay? So hidden in this definition, it's saying that the unit normal vector is never defined if it's going on a straight line. However, if it's turning, let's say, if it's really turning like this and they have this plane that almost contains this line, then in this plane, the direction that this is turning is where the normal vector is pointing. Okay? The normal vector is like trying to say, oh, this curve is turning. In which direction? The direction that the curve is turning is where the normal vector is pointing to. Okay. Now this is 3D, so if you have a unit tangent vector and a unit normal vector, it just gives you a plane in 3D, right? And that plane, given by the unit tangent vector and the unit normal vector, this one is what's known as the kissing plane. Because at this point, it's the closest plane to the curve. Right? So if the curve is going that way, then the unit normal vector will be pointing this way. If the curve is going like that, the unit normal vector will be pointing this way. If the curve is turning this way, then the unit normal vector will be pointing that way. Does that make sense? Yeah. Because this tells you how the curve is turning. Okay. Now, there's a third vector which is perpendicular to both t and n. That's called the, I forgot what it's called. It's something like this. I think it's t cross n. And these three unit vectors give you a frame that's moving along with the curve, which is known as the Frenet frame. Frenet frame. But we'll not go over this one. Yeah, that's more of an interest of geometry, differential geometricians. They use this Frenet frame to discuss further geometric properties. Rather than that, instead of talking about this third vector that's perpendicular to both, I'm going to talk about tangential and normal components of the acceleration. So let's talk about that. So now what I need to show is, let's talk about acceleration. The first derivative of the position vector is known as the velocity, and the derivative of the velocity is known as the acceleration. So it must be the second derivative of the original curve, right? Okay. Now, what I'm going to say is that AT, if you do the dot with the tangent vector, then this is going to give you some component. And this is what I mean by, I talked about this component of u to v is equal to u dot v divided by norm of v. That's the formula for the component, but I told you not to memorize it like this. You should really think of it as like u dot v hat, where v hat is what? V hat means this. You divide it by size, right? That's what it is, u dot v hat. And the reason that this gives you the component is because if you have u, and here's v, and here's v hat, then the dot product is, by definition, dot product is norm of u times norm of v times cosine of the angle between. But since this is 1, this u dot v hat just picks up this length. Norm of u will be this length times cosine of this angle. What's that? That's just perpendicular projection. Okay? So that's where this formula comes from. Okay, you don't want to memorize this formula, rather you want to understand like that, then there was no need to memorize. So look at what's happening here. This is already a unit vector. So if you want to pick up the component of A in the tangential direction, you just dot it with t. Okay? So what does that mean? If you have something that's accelerating as something, if particle is speeding up as it's moving, then it's going to have a tangential part. Okay. All right. So that's called the tangential component of acceleration. Okay. And then you can also do the same thing for the normal component. That's the normal component of, so you get the normal component of acceleration, which is, we denote it by a sub n. That's known as the normal component of acceleration. And what's surprising is that acceleration can now be written as at t hat plus a n hat, and that's it. Okay. So I talked about the Frenet frame. There's a vector that's perpendicular to both t and n, right? That vector is not going to pick up any component. So in other words, at would be perpendicular to k. Okay, so let me try to explain this later, but intuitively this is what it is. In the kissing plane, momentarily the curve looks like a two-dimensional motion inside that plane. So there is nothing that's like trying to get out of the plane. There's only two things. One, at, which is used for acceleration, and an, which is used for turning. Okay, so let me try to explain that further by examples, but my point is here. This is true, and this tells you two things: that tangential component of acceleration is responsible for speeding up or down. Okay. And the normal component of acceleration is responsible for turning. Okay, in other words, what happens if tangential component is 0 and the normal component is something constant? What would that mean? Well, because the tangential component is 0, it's not going to be speeding up or down, right? And then because the normal component is constant, it will bend at a constant rate. So what kind of motion would you get? It'll be a circle, okay? It'll be a constant speed rotational motion. Okay? That's what you're going to get for that case. What happens if nt is 0, okay? But this is tt is constant positive thing. If nt is 0, or I can't say it because let's say t prime t is 0. That's a better way to say it because this will be undefined. Right. So we will just say an is 0 if t prime t is 0. Okay. So I'm not even going to write it. Okay. So if this is the normal component is 0 and then this is positive 1 all the time, what does that mean? That means it's never turning, so it's going in a straight line. And because AT is positive 1, it's continuously accelerating. That's what it means. Okay, so that's what we get. Which means I can add those two things into our formulas that I already have here. So let me write it here. However, I want to talk about this one. This is misleading. One is misleading and useless in most cases. Okay. Now, why do I say that? That's because you saw how complicated n is, right? So for most problems, there's no way to use this to find the normal component of. I mean, you could try it after maybe 3 pages of calculation, but that's not a good idea. Okay. So instead of this, although you may have thought that this is not a big deal, the fact that these t and n are perpendicular to each other, and you have these two components for this a, means this. Like you can think of this as like the x component, that's the y component. Then if you have two quantities for the x and y component, how do you find the norm of a? You just set this square plus that square, right? So a nice way to do things is, okay, right. So a nice way to do things is, say, norm of a squared is a t hat plus a n hat dotted with itself, same thing, itself. But then if you do at t hat dotted with att hat, any vector dotted with itself is the norm squared, but what's the norm of t hat? What's the norm of t hat? 1. Okay. So this is going to give you 1, and you get at squared, right? And then when this hits the second guy, which is this guy, t hat and n hat are perpendicular, so that's going to give you 0. And vice versa. When this hits the first guy, it's an n hat dotted with at t hat. That's going to give you 0 because these are perpendicular. And then an n hat dotted with an n hat will give you an squared. So you get at squared plus an squared. And from here, you get an alternate formula which says that an is equal to square root of a norm squared minus at squared. Okay, and that's like 100 times better than trying to use this formula. This is like impossible to use, but this is a lot quicker. Okay, so let me show you this next example. Again, let's work with the same guy. Okay, find at and an at time t equals. Okay, so solution would be, well, we need the acceleration, so we'll have to differentiate it anyways. So differentiate once, differentiate twice. And then plug it in 1, so you know that the velocity at 1 is going to be 1, 2, 3. And you know that the acceleration at 1 is going to be 0 to 6. And since t hat is v over norma v, you're going to get 1, 2, 3 divided by square root of 1 squared plus 2 squared plus 3 squared, which gives you 1, 2, 3 over square root of 14. That's your t hat. And therefore, at is same as acceleration dotted with t hat. Acceleration, we got it at 0 to 6. Dotted with t at 1, 2, 3 over square root 14. 0 times 1, 2 times 2, 6 times 3, divided by square root of 14 is going to be 22 over square root of 14. So that's your AT. And now what? Do we use this formula? Well, to get that formula, I have to first divide this by its size and differentiate again, and we already know that's going to be terrible. Right? You don't want to do that. Okay. Yeah, that was my point for actually trying to show you the NT. It's just really hard to use. So rather than this, you use this one, which gives you AN as square root of, well, what's the square root of the A? It's 0 to 6, so 0 squared plus 2 squared plus 6 squared, minus this squared, 22 over square root of 14 squared. Okay. Now I feel like I need a calculator. Let's see, 36, 4. 40 minus 21, 484 over 14 square root. Yeah, this comes out as something terrible. Because even if I divide by 2, let's just do it. 280 over 7 minus 242 over 7. So that's going to be square root of 38 over 7. Okay, so that's the AN. All right, so any questions here? All right, so here, is the particle speeding up or down?
Speeding up.
This is positive, so it's speeding up. If this was negative, it would be slowing down, okay? Is this particle turning? Yes, indeed, it's turning. Okay. So that's what you can figure out from the acceleration. So it gives you the tangential and normal components of acceleration. Yes?
How can you tell if it's turning?
Because the normal component of acceleration, what's the normal direction? It's the changing direction of the tangential vector, right? And if you have a big value there, that means a big component of acceleration is being used to turn things.
Okay.
Thank you for the question. I forgot to say another thing. AT could be plus or minus. If this is plus, it's speeding up. If it's minus, then it's slowing down. Whereas for this guy, if this is always positive. This will always be in this acceleration will always be pointing to the same direction as the normal direction, in the same direction. Okay. Example 4. So here's a helix that we talked about, let's say 2 cosine t, 2 sine t here, but the very first one, I'm going to put a t squared. Okay. So it's like a helix. Right? If this is the x direction, it's like doing this, right? But the x coordinate is speeding up. So it's like if it was a spring, initially it's a spring that's wound tightly, but then the spring gets like elongated this way. That's this, right? So for this one, the question is find tangential component and the normal component of acceleration at t equals 0. Try that. So solution, you need the velocity, which is the derivative, which is 2t negative 2 sine t 2 cosine t. And you also need acceleration, which means you have to differentiate this again. And that gives you 2 negative 2 cosine t negative 2 sine t. Yes.
How many points in the test would that much give you?
Yeah, it's a really practical question. Yeah, I would say if it's a 10-point question, this will be like 2 points.
Oh,
That's it.
2 out of 10? All right,
Yeah,
let's go.
yeah.
4 out of 10.
And then,
Would you get
20 right there on the test?
Oh god.
What did you say?
No,
we'll let that.
bro.
What you say?
and then you plug in 0 to get the velocity at 0, and then 2 negative 2 is 0. This is the velocity,
How would that one?
4 points, right? Yeah. Or, no, all you did was plug in 0, so 3 points, 3 out of 10.
Oh,
Okay, now from here you say t hat is what?
V over negative.
Yeah, so it's 0, 0, 2 over square root of 0 squared plus 0 squared plus 2 squared, and that just gives you 0, 0, 1. Okay?
Ryan.
And then, oh, really?
Less.
Wait.
Tana. Dominic? Tana? Who's Tana? Who's? Tana. Or hurting him.
Okay. Really? Okay. So, did I get something wrong?
Say power damage.
Okay, seems right. Okay. So, therefore, what's the tangential component of acceleration?
It's
Just 0.
Yeah, that just gives you 0.
It is 0.
Okay, who else got 0? Okay, so I guess I'm right. Okay. I'm a little confused because if it's t squared, shouldn't this be accelerating?
Yeah.
If you differentiate twice, you get 2. So I thought that's going to be accelerating. Okay.
You know?
alright.
It's counter to my intuition, but I guess I'll have to accept it.
Right now.
Alright, so what is an? In that case, the square root of norm of this thing, which is square root of 2 squared plus negative 2 squared plus 0 squared, minus the 18 squared, but the 18 is 0, so that doesn't do anything. So that just means you get square root of 8. Right.
2 right, 2 right, 2.
2 right, 2. Well, that's the answer.
100.
Okay, so just let me conclude with the short remark that I had. So, how do you know that acceleration would just have only these 2 components, the tangential and this? Like, it doesn't have the third component with k. Okay? So why is this true? So let me try to explain that part. And the way you show that is by starting with t hat t equals to v prime t over norm of v prime t. And so I'm trying to prove that statement. And then you multiply this to the other side so that you get v prime t equals to norm of v prime t times t hat t. That's what you get. Okay. And what is v prime t? If you differentiate the velocity, what do you get?
Acceleration.
That is the acceleration, right? So you get the acceleration. No, sorry. It's this. What am I saying? Sorry. Okay, so step back. Okay. So let me just start over. Okay. So we have t hat t defined as taking the velocity and dividing it by its size. Right? And I multiply vt to the other side so that I get vt equals to norm of vt times t hat t. Now I want to make a statement about the acceleration. I have velocity, so what should I do? I differentiate both sides, right? So if I differentiate vt, I get acceleration. But on this side, it's a multiplication, so I have to use the product rule, which says I have to differentiate vt, norm, plus, and I have to do vt times t hat prime of t. Oh, this is a scalar quantity, right? And it tells you the rate of change of the speed. So not only this proof, when finished, shows that this is indeed true, it actually explains what AT is. AT looks at the rate of change of the speed. Is that good? It's the rate of change of the speed. Okay. And then over here, if you look at the definition of n of t, is t prime of t times t prime of t divided by the norm of it. So if I multiply this to the other side, I can rewrite that as norm of t prime of t times nt. So this one right here tells you that this one right here is ant. Okay. Now, what this also shows is that the actual stuff, this one right here, is the way that the curve bends. Right. This is more like the curvature. Okay. Bends. And because it just shows this is how fast the direction is changing, right? Yeah. But then look at this one. Well, it's saying that if you're going at a high velocity, then if you're going at a high velocity, then you need very big AN so that this increases. So it also means that if you're going at a high velocity, it's harder to turn. Yes. If you're going at a lower velocity, so if this is small, but this is big, that means this is very big, right? So that means if you're going at a lower velocity, then any normal component of acceleration is going to make it bend a lot. That's what this is saying, right? Okay, so now you have something times t hat and something times n hat equals at. This portion is now going to be called as at. This portion will be called an. And now what is to be proved is proven. You still have to see why this is same as that and that same as that, and that's simply taking this one and plugging into this formula. You see right away that if this entire thing is dotted with t hat, This will be 1 and this will be 0, so you just get this much. So they're the same. Okay. So the outcome of this is that AT is really norm of VT, right? And the other one too. That's all.